So, we are trying to explain about the fine structure of atomic spectra. So, we have considered single electron system and we have seen that energy E n j basically, that is n 1 plus z square alpha square by n square then n by j plus half minus 3 by 4. So, that was the energy expression which depends on basically only on n and j. And what is j? J is L plus minus S for single electron system. One electron, it has L angular momentum and it has spin angular momentum. So, they couple LS coupling. Due to LS coupling, it gives the resultant J. So, J value can take L plus minus S. So, for single electron, S is half, S equal to half, okay, S equal to half. So, now depending on L, L can be 0 for S orbital. So, then J will be, for this J will be half, then for L equal to 1, J will be L plus minus half means L is 0, L is 1. So, J will be half or 3 by 2, for 2 it will be 3 by 2 or 5 by 2. So, this way one can find out J value for corresponding defined L value, and this can be for any n equal to 1, 2, depends on. So, it does not matter whatever the n value, but for a particular n value, so it will have n number of L value, starting from 0 to n minus 1, right, that we have seen. And we have explained the fine structure of H alpha line, So, H alpha line. So, this it's basically from n equal to this transition between n equal to 2 and n equal to 3, and then it splitted into 5 lines. That is this H alpha line is composed of 5 lines, and that 5 lines from the transition, considering this energy expression which depends on J, and selection rule we have considered del J equal to 0 plus minus 1, right, and del L equal to, here we do not need, but it is plus minus 1, that is the another selection rule. And also we have seen the origin of the sodium D1 and D2 lines, sodium D1 and D2 lines. So, that for sodium outermost electron was in n equal to 3, right. Now, for n equal to 3, so L will be 0 1 2, L will be 0 1 2, L will be 0. So, this for sodium D1 and D2 lines. So, its outermost electron is at n equal to 3. So, you will get basically for n equal to 3. You remember that for L equal to 0, this is the S, L equal to, so there are 3 possible value, L equal to 0, L equal to 1 and L equal to 2. Okay. So, and S is half one electron in outermost, that is 1 electron. So, S equal to half. Okay. So, your J value, J will be half, and in this case L equal to 1. So, for this J will be half and 3 by 2. Similarly, for L equal to 2, J equal to 3 by 2 and 5 by 2. Okay. So, this term basically, so L equal to 0 means is S, I will get term for L equal to 0, it will be, I think, let me write here. So, for n equal to 3, so what are the term I will get? I will get L equal to 0. So, this is S, okay, and S equal to half, multiplicity 2S plus 1. So, it will be 2 and J equal to half. So, this is one term. So, it will have one energy level, and then L equal to 1, this is term P. So, P will have term P will have 2 J value, half and 3 by 2. So, this also 2, this is 1 half, this one term, and another term. Now, which energy will be lower for same S, for same n value, n equal to 3. So, that we have mentioned that when J will be higher, so this term will be lower. Okay. So, this term will be lower. So, 1 plus this, it will be lower value. So, smaller J, lower energy. Okay. Smaller J, it's it will be more negative, and higher J, this value will higher J. So, this value will decrease. So, it will be less negative. So, so 2 phi half and then another energy level you will get. So, that is 2 phi 3 by 2, right. So, transition basically from this level to this level. So, this one is d1, another is d2. Okay. So, earlier this when j was not considered. So, this two value d1 d2 was basically it was showing one line. So, you will get d1 d2 because of this LS coupling that resultant j. So, now that also we are able to explain. Next, what we want to see that anomalous Zeeman effect, whether we can explain anomalous Zeeman effect. So, normal Zeeman effect we have seen any lines it breaks into 3 lines, that is normal Zeeman effect, but in anomalous Zeeman effect Zeeman effect. So, different lines it split into in different number of spectral lines. So, let us check just sodium D1 and D2 lines. So, sodium D1 D2 lines, here you can see the sodium that is D1 lines, it is basically transition between these 2s half and 2p half, right. So, this transition. Now, when you apply magnetic field, small magnetic field, then what happens, that's what we want to see. So, there will be change of energy due to magnetic field. So, that energy this similar as we have seen earlier. So, that energy additional this term plus this additional energy due to the magnetic field. So, that is mj gj mu v b mu v b. So, earlier we have seen in case of ml or ms we have seen. So, in that case for ml gl that value was 1, gs that was 2, and now gj is different value. What is the gj value that we have derived? So, that was 1 plus j square plus a square minus l square by 2 js. Okay. So, for these two terms, what is the j value, what is the l value and what is the s value, that we know, and we can find out gj. Now, what are the mj value for a particular j value? Mj value again minus j2 plus j. Okay. So, here j equal to half. So, its mj will be plus half and minus half, mj will be plus half and minus half. So, it will be split into 2 level. Okay. mj equal to minus half, mj equal to plus half. Okay. Similarly, p, here j also half value. So, its mj again 2, So, it will be split into 2. So, what you will get here, it is minus half and this plus half. Okay. Now, here you have to consider this transition, this selection rule. In this case, you have to consider mj equal to 0 plus minus 1 and del j equal to 0 plus minus 1. So, del j already we have considered. Now, we have to consider the mj value. So, here you see this transition is possible. Let us take so del j has to be different, okay, and also one has to consider this, you see del L equal to plus minus 1, okay, and del j equal to 0 plus minus 1. Okay. So, here transition between these two is not possible because it will violate the same L. Okay. So, transition only possible between these two. So, that is fine, already we have considered. So, here transition between this level to this level we have to consider. So, this transition is possible because minus half minus half. So, it is del mj is 0 and then from here minus half to plus half also it is allowed because del mj equal to plus minus 1. Similarly, from here this plus half to minus half also allowed, and from here this plus half to plus half, this also allowed. Okay. So, now we can see this D1 line, it is splitted into, it will be splitted into 4 lines, and experimentally it is seen that this D1 line, it shows these 4 lines and their wavelength exactly match with the experimental value. Similarly, one can show that this when you will consider the D2 line, so it is splitted into 6 lines. It is splitted into 6 lines. So, here itself I can do. So, D1 for D1 it was P half to S half, that transition, and D2 transition P 3 half to S half. So, now it is D2 line, earlier we considered D1, now D2 lines. Now, here this is fine, but this one now j equal to 3 by 2. So, mj will be minus plus 3 by 2 to minus 3 by 2. So, we will have 3 value, 3 by 2, half, minus half, minus 3 by 2, okay, mj value. So, we will get more 2. So, this is minus 3 by 2 mj value, and let me erase it, and then I will get another value, that is plus 3 by 2, because higher mj value energy will increase, higher mj value energy will increase. Okay. So, this is the highest energy. Okay. So, and this transition also it is possible to see, you see these 2 lines cannot have the same energy because of the Gj value, because Gj value will be different. So, this splitting will be asymmetric, you know. Earlier in case of ML, this splitting was symmetric. So, we have seen that 9 lines for H alpha line. So, it is basically 3 lines, and that was because of this symmetric splitting. Now, this asymmetric splitting, because Gj value will be different for different j value, okay, although S and L value same, but j value are different. So, Gj value will be different, and then splitting will be asymmetric. Okay. So, in this case now you see, so now this transition will be allowed whatever we have seen already. Now, additional you see I have 2 more lines minus 3 by 2 and plus 3 by 2. So, minus 3 by 2 to half, this transition is not allowed because it will be 2, del mj value will be 2, so it is not allowed. So, this is the final minus that initial. So, plus half minus of minus 3 half, so it will be 2. So, this is not allowed. So, minus 3 by 2 to this minus half, it is allowed, it is allowed. So, del mj value will be plus 1. So, this will be allowed, this will be allowed, and from this level plus 3 by 2 to minus 3 by 2, this is allowed because minus 3 by 2. So, it will be minus 1 del mj. So, this is also allowed, this is also allowed, okay. Sorry, this is also allowed up to this, but from here to this minus half it is not allowed because minus half minus 3 by 2. So, it will be minus 2. So, that is not allowed. So, now you see it is 6 lines. So, and experimentally it is found that sodium D2 line is split into basically 6 lines. Okay. So, what we have seen that this considering the spin angular momentum and then their coupling, LS coupling giving resultant angular momentum J, that is quite successful to explain the all atomic spectra, whether it is fine structure or it is Zeeman effect, basically anomalous Zeeman effect. Normal Zeeman effect also is explained. There it is considered that when there is no existence of, and for that we have seen that we do not need to consider spin, okay, only L, considering L and ML. So, that was sufficient to explain. Reason is that this at high magnetic field, this LS coupling basically breaks. So, that coupling do not exist. So, there is no coupling, there is no J. Okay. So, individual S and individual L, they are independent. So, already we have seen that considering only L, one can explain the normal Zeeman effect, and S is there. In presence of S, it will not affect, because this energy that it depends on NL and whatever due to S. So, that will not affect the transition. So, thus this is the complete quantum number so far we have got. So, what the quantum number we have got for single electron N and then L and then ML and MS. Okay. So, if we do not consider the LS coupling, then these 4 quantum number is sufficient to explain the most of the properties, and one has to consider the J in that case. Then in that case we consider that when we are considering the LS coupling, then one has to consider J value instead of L value, one has to consider J value, then that is N, J, Mj, okay, and I think these 3 are sufficient, N, J, Mj value, okay. ms one we have to know, I think yes. So, yes, so n, j and m j, these values are sufficient. Basically, these three values will be sufficient. If I know the, I have to know the g j. So, either one should know S or L. If you know S or L, then other one can be find out, other one can be find out. Okay. So, this the basically picture of single electron system. So far whatever we have considered, so that is for single electron, and for single electron we have explained the different kind of spectral lines, that is whether in presence of electric field, whether in presence of magnetic field, or in presence of without any electric or magnetic field is normal. Okay. Now, we would like to study about the many electron system. Okay. We would like to study about the many electron system. Or multi-electron atom, many electron system, or we tell multi-electron atom. So, more than one electron in an atom. So, then what about the spectral lines of those atoms? So far we have seen the spectral lines for single electron system, we have studied the single electron system. Okay. And there we have seen that what is N, what is L, okay, and what is J, what is ML, what is MS, MJ, and then let me write this is S, this is J, ML, MJ, MS, right. So, here two aspect, one is when there is no LS coupling, electrons this angular momentum are independent. Okay. This is one aspect. Another aspect, when there is a coupling between angular momentum and the spin momentum, then scenario is different. Okay. So, in most of the cases, it is this coupling is observed, and considering the coupling, considering the resultant J value, and we have seen that one can explain all phenomena of spectral lines. And this atomic spectra, study of atomic spectra, basically spectroscopy of atoms. So, that is very helpful to study, to find out the structure of the atoms. Structure, what is the structure of atoms? So, you have nucleus, then electrons are surrounded. So, how they are rotating or revolving around the electrons, around the nucleus, and So, they are rotating in different energy level, okay, different orbits, orbitals, and these orbitals, they what is their energy. So, that everything we have studied. So, now if we take helium atom, so it has 2 electron, basically it has 2 electron, right, and then lithium is basically alkali atom. So, in case of lithium alkali atom, that is equivalent to 1 electron that we have seen earlier. So, it is multi-electron, but it behaves like single electron, why that we have explained. So, this then beryllium, this 4 electron, then if you can take any one, say silicon, it has 14 electron. Okay. So, now multi electrons, more than 1 electrons, for them how we can study the atomic spectra, or how their structure, how the electrons are arranged in the atom. So, so that we would like to study. So, I will continue in next class. Let me stop here. Thank you.